So hello everyone, my name is Jia Rui. Many of you know me. I am the host for today's seminar and also I am a volunteer at Dashu. So we have Wujua Ratan from Amazon team today joining us. It's been a great pleasure to have him here. I'm going to come down to introducing him in a second, but allow me to use this few minutes to introduce ourselves. I also love to make a quick announcement, a big thank you to our sponsors. So we are a 501c nonprofit organization that was founded almost 8 years ago. I became a volunteer at year 3. Oh my God, time flies, right? And in the past, less than a decade, a lot has happened in the data science field with the advancement of AI technology. And we're dedicated in promoting data science through our communities. So many of you sign up as a community member of Dashu member through our email blasting service. That's how you guys are able to join the seminar today. So everybody welcome. As Dashu, as a volunteer, I actually joined a very happy and big family. Here is a snapshot of our board members as many great volunteers with all of their dedications and commitment. We're able to deliver great online seminars like this one that you're attending today. Many thanks to our volunteers who do the honors job. And also, again, big shout out to the audience. We need your help. We're looking for great volunteers to join us in the future. We are getting more and more attentions. There are more subscribers and members to be joining every day. We need your help. If you're a young trainee in the school doing your grad work, or if you're a professional working in industry or academia, reach out to us. You can find all of the contact information, through all of the major channels. You can just leave us a note, shoot us an email, or you can just even search my name on LinkedIn. I'll respond to you if you're interested in joining. And again, we cannot survive without any of the generous donations from all of the major parties, our industry and academic collaborators, and all of the individuals like you. We need your donations to help run our email blasting service, help run our social media channels and websites. So that's why it's my great honor for today to announce Beijing has been a great sponsor and very generous to sponsor today's seminar as well as our upcoming seminars. Thank you, Beijing, for your very kind and generous donations. That's why we are very happy to help you promote the Beijing values here. You guys can definitely see as a global commercial stage biotech company, Beijing is, that focuses on discovering, developing, manufacturing, and commercializing innovative medicines. Here, the 4 core values are the patients at heart, patient first, collaborative spirit, bold ingenuity, and driving excellence. Thank you for your kind donations. And also, as a nonprofit dedicated to promote data science, we're very happy to see our sponsor is also a key player in the field that innovates towards a state of data science excellence that delivers real-time informed data-driven decision-making. I do believe I've talked with Jingjing, who is here from Beijing, joining us on a session today. Data excellence is a core foundation that Beijing holds. They actually developed this amazing app called B1. Check out this one. The B1 is a super app for drug development that comprises interdependent business-driven products built upon clinical enterprise data acquisition repository, with the ultimate goal being able to empower and accelerate business functional teams to derive real-time data insights and make data-driven decisions. And that's why, we're very happy to have Beijing sponsoring us because, we are also dedicated in promoting data excellence with, we share the core same values. So check out this digital platform, data strategy framework that Beijing is promoting here. So again, last but not least, we cannot survive without your donation. Thank you, and also thank other members who donate to us. This is a great example of collaboration between a nonprofit organization and a pharma who's also dedicated in data science. So please join Beijing, check out their websites if you're interested, if you're a data science, a data analyst, clinician, or you do IT work, check out their websites. This is a great place to work and great place to be. So without further ado, I would love to come down introducing Wujun Ratan from AWS. Today's topic is generative AI for healthcare and life sciences on AWS. I'm sure he will touch base on foundation models that powers the generative AI under the AWS framework and how we can leverage all of this to address domain-specific questions. Wujua is definitely a great player and leader in the AI within the health industry. So he's a leader for the AI and machine learning data science team in the AWS healthcare and life sciences business unit. He himself also is a solution architect of artificial intelligence and machine learning. He has years and years experience delivering medical products related to medical imaging, clinical records and genomics under the scope of AWS. And I can't wait to hear more about it. I know we have a big audience joining us today, so I'm not going to waste everybody's time. Wujua, I'm going to hand over to you. Feel free to share your screen right now. Thank you very much. And thank you for coming to giving us a great talk. So it's all yours.
Thank you. Thank you, Jerry. And thank you everyone at Dashu for inviting me. I do want to begin by acknowledging all the great work that Dashu is doing through the volunteering that you all have done. So amazing job and congratulations on that. So let me share my screen. I hope you all can see it. So I'm gonna, go over this presentation, sort of describing what generative AI is and some of the use cases that we have seen in the industry that I have been personally engaged in, and how it's actually creating a difference in the way clinical workflows are run. And then I'm also going to get into some key considerations, because there's a lot of misconceptions out there about how to evaluate the best approach or the best model that you would want to use for a particular type of use case. And then I'm going to conclude by some specific innovations and services that we have created to make all of that consideration very easy for you. So as a business user, you do not need to worry about the underlying details of some of these workflows, and just concentrate on the value that you want to generate in your own businesses. So as was mentioned in the introduction, I lead machine learning and data science for healthcare and life sciences at AWS. I've been at AWS for about 8 years now, so playing various roles, like started off as a solution architect and then took on this role of being a principal in machine learning and healthcare and life sciences, and now lead a team around that same idea. And over the past year and a half, I have been leading efforts around generative AI and its application for healthcare and life sciences, not only from a point of view of our perspective. When I say our, I mean AWS's perspective on this problem, but also trying to build some knowledge share and ideas around how to take this to regular clinical workflows, because there's a lot of misconception, as I said earlier, about the potential of this technology. And while people see great reactions come out when they ask questions to these pre-hosted service-based models, and the verbosity with which it responds, it's very difficult for you to coalesce all of that into a clinical use case and see the potential of it with all of the regulatory and privacy challenges that surround it. But if I have to begin by answering the question what generative AI is, it is a technology that allows you to create or generate new content, right? So these content could be in different sets of modalities. It could be images, videos, text, and these are all powered by very large models, as we call them, foundation models. And these models are actually trained at internet scale data sets. So what I mean by that is these are data sets that are available in a variety of formats across the internet. They're not necessarily fairly well indexed. And these models have the potential to actually learn correlations between the data points that is exposed in the pre-training step. And in a lot of cases, you would see these foundation models begin with an exercise of pre-training with very large corpuses of data, the model parameters reaching up to even a trillion parameter model now, but having the ability to kind of be fine-tuned on that pre-trained model for very specific tasks. And that fine-tuning is where I think a lot of customers in healthcare and life sciences are very interested in, because if you think about a large model that doesn't provide a lot of information on where the data sets that it's trained off exists, how real they are. There's a lot of potential for those models to be giving you wrong answers, and there is very difficult. It's a long and difficult path for you to verify those answers. So that becomes one of the key considerations to begin with when we say customizing your FMs or foundation models for very specific tasks in a way that you can explain how the outputs are coming. And there are ways in which you can do that, with workflows that I'll share later in the presentation. But if I have to think about how this technology can be applied in the life sciences industry, it begins with early research and drug discovery. As you know, this is a very trial and error oriented process where you're searching for millions and billions of molecules and trying to identify which molecules are candidates that you can take into further clinical development. And this process can be short-circuited by some algorithms that have been produced specifically in the protein space or large molecule space. Even in small molecules, we've seen a lot of foundation models that can predict standard properties of models, like its toxicity, its solubility, which are all necessary for you to determine whether it's a candidate for further development. In the large molecule space, obviously protein folding is of a lot of interest. All of these models like ESM fold, which is a folding algorithm that's built by the Facebook research group, is now in open source and can be derived into a variety of problem solving in the molecular modeling space. So not only in the folding space, but using those same model embeddings and trying to fine tune them for different tasks, which is a very common pattern that we've seen. And the idea behind all of this is that while you are not conclusively reaching a target, you are shortening your cycle of discovery and design with these tools, and how you use those tools in your workflows is extremely important. As you go along, you see clinical development. So in the space of clinical trial, we've seen a lot of documentations being generated in terms of your protocols, developing intelligent protocols, trying to learn from previous mistakes of trials that didn't succeed. All of those are things that generative AI can help with. In the manufacturing space, obviously predictive maintenance is a big use case. We are seeing machine failures being offloaded into foundation models that can predict from patterns and when the next failure is going to be, and take actions to sort of prevent that. And of course, resource optimization overall, not only in terms of machinery, but also people, trying to make them more efficient in what they're trying to do. In the space of commercial affairs and commercial and medical affairs, one of the things that's of a lot of interest to our customers is how you are actually solving for the patient outcome prediction problem. So if you are working with patients with certain risks, how do you prevent from a bad outcome to happen? So let's say a chronic diabetic patient that has a risk of kidney failure. There are particular data points in its care journey that you can take into account while making decisions to prevent that from happening. And the sooner you can discuss and detect all of that, the better it is for the patient. And then of course, in the post care scenario, you are looking at a lot of use cases around trial matching and patient care concierge to provide post care support. Similarly, in the space of healthcare, there's a lot of clinical documentation out there that exists in the form of unstructured data sets. These could be text, audio, images, and they are all in very different modalities. And it's hard for any small model to actually derive correlations across all of these different data points that exist in different formats. So the ability for these foundation models to do things like trial matching, multimodal data analysis, creation of a longitudinal patient, doing outcome prediction, as I said earlier, and then remote patient monitoring, all of them actually correlate really, really well with foundation models. We have seen, a lot of success even on the AWS side when we are approaching these as problems, because when we are thinking about creating services, you might be familiar that AWS provides a lot of services, which we call managed services. And these managed services are all designed based on the patterns like these, which we are seeing in the industry. So for example, if there is an operational efficiency that we can introduce for clinicians who are actually trying to search through medical records, we might consider that as something that we can build on behalf of these clinicians, so they don't have to worry about building it. And that's how the essence of AWS services, or the genesis of AWS services, happen, by working backwards from some of the ways and patterns that we've seen customers actually ask us of how to create some of these workflows. Now, one of the biggest misconceptions that we have seen is, as I was talking earlier, was about the fact that bigger model is always better. Well, that's true for a lot of generic tasks. So if you're like asking it to write a story about, a particular event, then it'll do a very good job of, writing a verbose story. Or if you're asking it to write an email, it may
hold on. Yeah.
Sorry, I'm gonna have them muted.
Yeah, so I think large models are great for a lot of generic tasks. But when it comes to a domain-specific task, which is what we are talking about today, there's a nice research done by folks at MIT that arrived at a conclusion that it's not always better to actually go with very large models when it comes to domain specific tasks. They also said that in context learning with extremely large models, very large, very small models that is specifically tuned for a particular problem. And that's where we see the biggest potential and opportunity. While large models might generate a lot of interest initially, and you might see good results, there are some inherent problems with those models. Like, firstly, it's very hard to maintain a large model. As you get larger and larger, you would see that the latency in these inferences would start increasing. And while you might be using its knowledge of the world to actually generate verbose responses, those knowledge of the world is actually very shallow when compared to a smaller model that's very deeply trained on data set for a particular domain. And that's why their finding said that it's not comparable to fine-tuned models. Fine-tuning a very large model is also very hard engineering-wise, because you have to think about like innovations in terms of how you distribute that model in memory. How do you load those models and fine-tune the parameters of those models? It's not a very easy task to do when compared to like a smaller model that can fit into the memory of a single instance, and then you may be able to get better results for a particular task. So having that as the cornerstone for some of the discussions we have had, we have arrived at the conclusion that model selection is a balance. It's not really dependent on just the number of parameters, but it should be determined by the combination of these three, which is the quality of the output for the problem you are looking to solve. The model quality might be very good for a generic task and it can be validated by humans. But if you are a clinical trial expert, or if you are a medical researcher, or if you are trying to like develop the next protocol, or you're trying to match the right patients to the kind of inclusion-exclusion criteria that you have in your trial, that quality is what you are looking to actually get out of a generic model. And that's where I think large models fail, because then it's not very easy for it to even if it is easy, even if it is going to give you the response you're looking for, it's not easy for you to derive latency and cost metrics in an efficient manner for those kinds of models. So as you start going bigger in, let's say, the amount of parameters, you would see a hit on your cost and latency. And the output quality might actually be generically very good, but domain-wise it may not be as up to the mark as you need. So striking a balance between these three and how you actually decide your model selection is a key aspect of your overall generative AI choices. The other thing I wanted to get into is that it's not only about model choice. Like in a lot of cases, we see customers mention that I want to just go with the best model. Well, that's obviously a very critical piece of the puzzle, but it's also about how you're operationalizing that model choice with some of the other things that you build around it. So for example, is the choice of your model coming from its ability to be fine-tuned on your own data? Or is it coming from your ability to actually maintain different versions of the prompts that you can prompt it with? As you know, like as you start like going from down to up in this list, it gets more expensive and more difficult for you to actually maintain these patterns. So these are all considerations that will play into your overall choices and the kind of use cases you want to build and the platform you're going after. So let's plot this in a very simple graph. This is obviously not drawn to scale, but if I have to on the y-axis think about the ease of use, right? So coherence and in-context learning. And then in the x-axis, if I have to determine cost and scale, complexity, this is how these rank, right? So on the number one side, the easiest for you to do is to do something like prompt engineering. And prompt engineering, essentially means asking the model the same question, but in a very different way, giving and the model actually giving you very different responses. So if you ask a model, explain what a clinical trial is, like you explain it to a 5-year-old, it'll give a very different answer versus explain what clinical trial is to an expert clinical trial researcher. It'll give a very different response, right? So having the ability for you to version it, maintain it, and provide contextual prompt engineering is the first level of customization. Then the next level comes into the space that we call retrieval augmented generation. And it's generally like 3 steps, right? Like you retrieve something, then you augment your prompt with that retrieval, and then you send that augmented prompt or customized prompt to a model that then generates a response. The cool thing about our RAG or retrieval augmented generation is that it doesn't require a lot of machine learning expertise, but it does require you to maintain some context somewhere outside of the model that can be augmented into a prompt. So I'll get into the details of that. Then you have the space of model fine-tuning. This is where you are actually taking a baseline model and then maybe adapting it to a certain task. So it can be, with some labeled data sets, you're training a baseline model to then only do named entity recognition or only summarize certain results. So these are all things that you can achieve with fine-tuning with a baseline model. The advantage here is that obviously you're not like spending so much time computing the results, because your data set on which you're fine-tuning is pretty small, and you're already relying on the knowledge that the model has gained from its baseline training job. And then finally, it's training your own model. That's obviously the most complicated, and it's also the most customized way of getting to the results that you want to get. Now, let's look at each of these in a little more detail. So contextual prompt engineering is essentially an idea that in this example, like you see, you start like the end user who's actually getting exposure to this model will just write some instruction to the model. So in this case, it says write a paragraph explaining a certain disease, right? Now, in the context of the model, that's not enough. So what you're essentially saying is, I want to now build a prompt template. So this is the key step that happens behind the scenes, where there are solutions that can take the question from the user and then append it with a lot of pretext and post-text to create like a template that the model can then understand. And that template is then sent to the model for a response. So in this case, as you can see, there's a lot of verbose instructions added to the model. And this is a key, and the difference that a prompt and a word in the prompt can make to the response generated from the LLMs starts getting more and more, I would say, it starts making a more and more difference when the size of the model increases. So if you're like working with smaller models, you might not see a lot of difference with like certain variations in the prompt. But if you are working with models of like, let's say GPT 3.5 or, even, Anthropic or Claude or all of these larger models that you'll see, the amount of difference that you would see in the response could be huge. And that is partly the reasons that people try to like limit just simple prompt engineering generic, in specialized use cases, because there is very little control that you can execute these to your satisfaction, because a small change can make a huge difference and you don't have a lot of control on how you send these to the model. The other thing to worry about here is, as these responses are being generated, it is also has the potential of making things up. So there are some evolutionary capabilities that gets introduced in these very large models, and it can start hallucinating. It essentially starts making things up, and that's also a problem with just like prompt engineering. This is also known as zero shot learning. So in this case, you're not giving any examples to the model. All you're saying is an instruction, and then supplementing that with a template to be sent into a model. The second approach is retrieval augmented generation, or in-context learning, where you're giving the model certain context. Now, what happens is, in addition to the instruction, the user, the behind the scenes, in this case, the prompt is also appended with some contextual information. Usually, these contextual information actually comes from a data store or some sort of an index outside of the model or outside of a template. So this could be done in the form of an embedding data store. So in that case, when the question is being asked, that question is being then compared to a set of embeddings that is stored in an external database, and then trying to find similarities between the question and the documents that actually may have the answer to what you're looking for. And then that entire context with the embedding is then sent into the LLM for summarization. It's a very common pattern. The advantage here is that you reduce hallucination, because you're guiding the model to actually only answer with the context you're providing it. You're also relying more on the skill of the model than the knowledge of the model. And that's a very important concept that you will see come again and again in your choices of the workflows that you're trying to make. So when you're relying on the skill of the model, what you're essentially asking the model is to summarize or answer a question based on a context. When you are thinking of model knowledge, when you're relying on its knowledge, you are essentially asking it questions that may not be directly derivable from the prompt template that you're giving it. That means you're not giving it a lot of context. And in those cases, you see a lot of difference between generic tasks and specialized tasks and its ability to generate and hallucinate. RAG is actually a good middle ground where you're solving for that. But before I move ahead, I thought it would be a good idea to just cover what embeddings are, because that is a very important context when it comes to RAG. And in a sense, what embeddings are mathematical representations of documents, audio, video, images, text, any sort of multimodal data. And it's usually works through a pipeline where you go through a method of tokenization. So you take all of these different data sources, you extract semantic elements that may embed knowledge, and these semantic relationships are then embedded into a large language model for embedding generation. These embeddings are generated again by models that can look at these different semantic elements and define relationships between them, and they are then represented in some sort of a vector or a matrix. These vectors are then stored in a vector data store, and then can be utilized for downstream semantic performance or similarity search. This is where I think the RAG approach actually wins from just like a simple prompt engineering, because when that semantic similarity search is done based on your question on a vector database, you only get semantically similar embeddings that is then sent into the model. One thing to note is these embeddings are actually multi-dimensional. It's like very highly dimensional. It's very difficult to visualize them. But if you do some sort of an dimensionality reduction on these embeddings, you can then visualize them in a 2-dimensional or 3-dimensional scale. And that gives you the ability to see how they are organized in the space, right? Like in terms of their closeness to a certain other word or a paragraph. And that's kind of the essence of embeddings, because it preserves a lot of knowledge and similarity and context between different paragraphs. Now let's move to model fine-tuning. And this is where I think the more domain-specific things come into the picture. So one of the reasons why you may want to fine-tune is for domain adaptation. So what I mean by that is when you think about a large language model and you're thinking about, making use of that model for a very domain-specific task, and that baseline model has not seen in its training a lot of domain specific data. So let's take a very simple example. If you go to Hugging Face today and you look at different models that are available in the LLM space, you will see a lot of these models tell you how they are trained. So which data sets they have seen. And let's say you pick a model from that group and you want to, generate clinical summaries from that model. It may not do a very good job. And you might think, well, I mean, I may have to go and increase the size of my model, right? And that's will prevent me from, getting these bad responses. There's also a method for you to actually look at that smaller model to be domain adapted with or fine-tuned on very domain specific data. And that is, a pattern that we've seen a lot of these organizations take instead of like going and increasing the size of the model just to potentially increase the quality of the responses. So it goes back to the three, pillar that I was talking about in terms of model choice and how you actually define which is the right model or the choice of the model for you. In this particular case, a good example of fine-tuning or the need for fine-tuning might be in the ability to, let's say, use a large language model to interpret properties from a proteomic amino acid sequences or a genomic sequence, right? We have been, looking at open source quite a bit in this space. There's a great set of open source algorithms out there that we've seen, perform really, really great, starting from AlphaFold. That was released by DeepMind. Then OpenFold, actually a true open source version of AlphaFold that was released by Columbia University. And then going into protein design, RF diffusion, you can see that this list is continuously growing from the open source community. And what we decided to do is, instead of worrying about which is the best model out there, we thought of like packaging all of this into a nice deployable solution that you can choose from all of these models, which are nicely packaged, and be able to run jobs with them. So if you're thinking of building your own drug discovery or design workflows, it becomes very handy when you have an API that we have created for you, and you just choose which models you want to run with an input data set. Like in a lot of cases, this relies on, let's say, a sequence of amino acids, and then you just send that into a model and it'll run behind the scenes without you worrying about the infrastructure details, and it'll come back with whatever is the output. In case of ESM, it'll come back with a PDB file, which is the structure of that molecule, right? And then you can take that structure and maybe go into a protein MPNN exercise when you're saying that this structure and a set of molecules, I want to find out which is the most which are the other molecules that would bond to this structure, and that is how you create workflows. And while there is not much you can do in terms of influencing the outputs of these models, but stitching them together into workflows is the key over here, which is what we are trying to solve for when it comes to fine-tuning. And then when it comes to training your own model, that's where you have to think about a few things when you're thinking about building your own model. So first one is the advantages. Of course, the great advantage of training your own model is 100% control of what the model is trained on. That's very, very important, which we want to like completely rule out any concerns about that model being exposed to data sets that you don't want it to be exposed to, or having control over your data sets, your proprietary data sets, not getting leaked out into a third-party model. You may also improve domain-specific accuracy if you train your own model. And then it'll also give you or your regulators confidence, because then you have a very transparent view when it comes to regulatory aspects of pharma workloads, where you're trying to like show from audit trail perspective, like what are the data sets that, and what are the versions of the data sets that went into the training of the model. Those are very important considerations, to keep in mind, but obviously there are some factors that you have to consider. First is the cost. If you're training very small models, it may not be that much of a dependency, but as you grow more and more in terms of parameters, the costs would actually play a major role. The other thing to think about is, do you have enough training data? Because like in a lot of cases, you may not need to train your own model. You may, if with limited training data sets, you can go into the fine-tuning approach or the RAG approach and still get very compelling results. And the last thing is that if you are investing in training your own model, think about the strategic importance of that to your business, because there will be a certain amount of resource, time, and cost commitments that are involved in training these models. So all of these are considerations sort of to think about when you're going into this space. So that sort of gives you a very good snapshot that, as you're like thinking about strategies of which model patterns that you have to choose for your own problems, you have wide range of choices to get to. So a good way to summarize this is in this chart, where you are going from option 1 to option 4. Option 1 being the least, I would say, invasive, because you're just like using the model's ability and its knowledge, to do prompt engineering, and there are a lot of benefits to that, because all you're doing is calling the model with different ways, and it doesn't require a heavy lift for you to get started. But there is trade-offs like hallucinations that kind of play into your decision-making prospects. So I would say contextual prompt engineering is great when you're thinking about an out-of-the-box model for generic tasks that does not require very domain-specific things and are low risk. Like even if it hallucinates a little bit, you're not like at a risk of a catastrophic, outcome. Like this is not directly making, for example, into a clinical decision-making process. So in those cases, maybe contextual prompt engineering might be fine. The other thing is retrieval augmented generation. As I said, this is a good I would say, a good middle ground where you're like using a lot of capabilities of the pre-trained model, but you're also using some engineering to give proper embeddings or proper knowledge to the model to make the hallucinations a little less. But there is still this overhead of response and latency, because as you're going more and more into RAG, especially when you're using for chatbot applications, right? You might need to preserve the context of your previous chats as you're conversing. And with in context learning and with RAG, your length of those prompts are actually going longer and longer. So if your history becomes longer and your models that you're actually sending these RAG prompts to are also being built, let's say, from token limits, then you really run into problems of chunking. There are engineering problems, or also cost problems related to those costs. So there are ways to get around that, but there's still, an overhead on that engineering wise that you have to think about. And then, of course, fine tuning with pre-trained models is also a great idea. It avoids complexity of training your models from the ground up. But there is higher costs and data management, MLOps considerations required for that. And then, as I said, the last most invasive way is training your large models yourself. And it's the best option for you to actually think about domain specificity. But obviously, as you get to the last stage, your complexity of maintaining that pipeline and the incurring costs, especially at the initial stage, is very high. So now I wanted to get into some details of what Amazon provides in this space. I know you can get a lot of this information online, but I wanted to summarize a few that we announced very recently. Hopefully you find some of this useful in your own work. So the first thing I wanted to call out is Amazon Bedrock. It's the easiest way to build and scale generative AI applications with foundation models. We have ensured that all of those considerations that I mentioned about earlier are taken care of in very managed ways when you're going through that journey of building your own applications. So some of the key features that Bedrock provides is an access to a range of models. So we believe that one model will not fit all use cases. As I said, in some cases, you might want to depend on a smaller model, which is fine-tunable. In other cases, you might want to depend on very large model that you're just doing zero-shot learning on. And all of those are options that you can think about when it comes to Bedrock. And privately customizing those models is also very important. We also had a lot of concerns from the customers that we were speaking to initially around security and privacy. We saw instances of, let's say, inference data or training data ending up in the models, training data, and being exposed to other customers. That's obviously catastrophic for someone who's trying to like use these models for very IP related tasks or tasks that are very private to an organization. You can't do that with models that can expose any of that. So we have taken care of all of that pipeline behind the scenes. We also have the ability to build agents and execute workflows based on that. And then we have made it very, very easy for you to use technologies like RAG and provide you the best price performance and managing infrastructure for this. So how it works, you basically is a very, very simple API to use, or it's also available from the console. You basically get into this console and you choose from a leading FM that we provide. You either customize it with your own data or connect to different data sources to enable task execution. These are the models that the Bedrock service provides currently. So it includes our own model, which we call Amazon Titan, which comes in both text and embeddings format. So you can use Titan for like text summarization generation, or also use Titan for generating embeddings for your documents and storing it in vector databases. We also have a choice of models from a variety of third-party providers, including AI21, Anthropic's Claude V2, which is unique because it has one of the highest context limits anywhere in the industry with 100,000 tokens. And then you have Cohere Command. Meta's Llama 2 is coming soon, which will allow you to sort of just call these Llama models with your own data sets and fine tune them. And then the industry leading text to image generation model called Stable Diffusion is also available. One of the things that has been, addressed as part of this service is your choice of selection of these foundation models. And what we have seen is when these foundation models are combined with tasks and the interpretation of that task, it is able to solve very complicated problems. And that's why we launched something called knowledge base. And with knowledge base, what you are able to do is connect these foundation models to your own databases and your data sources, and then use one of the vector or document databases that we have. Pinecone and manage Pinecone, all of these different options that you can then create embeddings for. And then, with the ability for you to then take that into a chatbot exercise, you have, full control on that RAG workflow. So now you're not only relying on the knowledge of the model, but you're also augmenting it with context from your own documents and sources, which makes it really, really interesting in terms of how easy it is to build, let's say, chatbots or summarizing use cases on your own data sets. One of the things that we also have is the ability to connect these to your custom-built AWS services that are specialized for healthcare and life sciences. So if you think about Amazon agents in context with some of the specialized services we have here, you will have the ability to connect it to, let's say, Health Lake, which is a service that we have launched that's specific to healthcare. It allows you to store all of your healthcare records in a centralized database, and then connect that to agents to answer questions based on patients. You can also connect Health Omics, which is a service that allows you to store genomic information. So all of the variant information, VCF files can then be stored into this service and connected to the Bedrock agents. Similarly, Health Imaging is a service that allows you to store radiology images. And with the ability for you to connect all of these three different data sources into a Bedrock agent, you can then ask it questions around, let's say, give me the conditions that a particular patient has, and then correlate it with this genomic information. And then with that genomic information, if you connect it to an external database, let's say clinicaltrial.gov or PubMed, you can even know more about the research that is done about certain variants that patients might have, and then correlate that with their imaging information. So all of this is seamless, in terms of your execution and the ability to actually read information from all of these doses. We also have a new service called Health Scribe. This is an audio modality service, so it allows you to create an endpoint and an API, which you can then give to clinicians. And as the conversation is happening between the patient and the clinician, it will auto-generate the transcript of that and then summarize it to be inserted into an EHR in a format like a SOAP note. So that is a very interesting use case that we have fine-tuned some of the Bedrock models to actually, address that problem in the clinical space. We also have the option to interact with dashboards in a conversational manner. So this is a new feature that we have launched under the brand of Generative BI. So QuickSight is a service that is our dashboarding solution, but you can then ask it verbally to create graphs and charts or alter the color of graphs and charts, and it'll automatically do that for you behind the scenes using a large language model. You can also extend it to create beautiful stories. So let's say you have a lot of data sets that you're then exposing into QuickSight. You can ask it to create a narrative or a document, and it will automatically go behind the scenes, pull out all the graphs and charts and summaries from your data set, and then create like a template for you to then be shared by external users. I wanted to conclude by some considerations on why it is hard to build generative AI responsibly, and this is the approach that we have been taking just to allow for customers to not think about all of these things when they are thinking about their business problems, because your attentions are better spent in talking about which services from AWS or any other platform you want to use for solving a problem, rather than thinking about what are the underlying security and privacy concerns that I have to think about. And one of the common things is fairness, which is very hard to ensure because you don't have a lot of control over how these models are trained, because they are very open-ended and broad, in their approach. So some of the things that we have come up with are categories around hallucination. So what is our approach of reducing hallucination? How are you ensuring that the data set is completely unbiased? How are you ensuring that there is a reduction in terms of toxicity and safety in the response from the model, or even to the input that you are sending to the model, so it's not getting influenced? How you're ensuring that your intellectual property are not being exposed, and how's your data remaining private? There's a nice blog that one of the Amazon scholars actually wrote on these topics that is available on that link. And then our approach to all of this is to ensure that we are building all of the generative AI applications and services in a very responsible way from the ground up. And it starts from thinking about generative AI, the responsible generative AI as a practice that not only applies in theory, but also in the services that we have built. It also goes into integrating generative AI into an end-to-end foundation model lifecycle, not just worry about the model training and inference, but also think about how is your RAG approach secure? How is your prompt template secure? I think a lot of this also depends on education and awareness. So prioritizing that through trainings and seminars like I'm doing today is also something that is a priority of ours. And then advancing the science behind the scenes, working with researchers around the world. We have a very thriving Amazon scholar community where we invite leading professors and thought leaders to actually come and join us for certain periods of time on certain very high impact projects, and take all of those opinions and translate them into AWS services that can benefit you as a customer of AWS. And in practice, as I was saying, not just in theory, but in practice, we have these constructs that we have built from the ground up, and they are all integrated into the AWS ethos. Right? So it starts with a virtual private cloud that actually is not something that you're going, interacting with public internet on. This VPC is sort of a boundary from the public internet that you can store your private information within, and Bedrock APIs all work within the context of a VPC. Model fine-tuning is also something entirely private. We introduce another layer of security on top of it with encryption. So all of that allows you to actually privately customize your models, and that model remains unique to you. And not just with Bedrock, we have over 300 security services and features that we have support for to ensure all of this is getting built in a very responsible and managed way. So I want to spend 2 minutes in just concluding in terms of best practices. I think it's always very important to begin with a use case, not think about generative AI as something that can do it all, and not get swayed by very large models that give you very verbose responses, but think about use cases. The more specific, the better. Also prioritize education awareness in this space. This field is very new. A lot of people have very different and strong opinions about this, and it's very difficult to get swayed by one of these thought leaders, right? So if you're not generating awareness, if you're not going to the right sources of information, it is very hard for you to wrap your head around this. So think about a strategy on how you assimilate information, how you share information on this topic. Do a risk assessment if generative AI is right for you, because it may not be right for everyone for a lot of regulated workflows. So think about that. Continuously test because there's no replacement for that. An iterative approach to building generative AI applications is extremely important. And then lastly, governance and accountability. How do you ensure that this is, if someone or some auditor is asking you questions about this, how you're responsibly answering those questions, and what is the data you have to prove those answers is also very important. So with that, I wanted to conclude today's presentation, and thank you again, everyone, for joining. I don't know if we have time for questions.
Well, why not? Let's do that. Thank you, Woodrow. This is a really informative and very interesting topic. Let's get down to the questions. I do have Milan asking, can you give us an example of models that you have built in the clinical development space? I don't know
Yes.
if you mean by early stage or late stage. Yeah, just give us like a model example in that respect.
Yeah, so with the services that we have at present, there is no model that is specialized for clinical development yet. Whatever we are doing is in the space of fine-tuning. And the fine-tuning capabilities of Bedrock that I explained earlier are things that we are relying on a lot of these customers to actually build and fine-tune their own models with. So instead of taking the approach of us building a model, which we can, because I don't think that is what the industry is looking for in terms of a gap. I think a lot of industry folks have expressed interest that we want capabilities to actually build it ourselves and host it as a managed service so that anyone can use it. And that is the problem that we are trying to solve, because a lot of models exist out there and that space is getting crowded. So how do you take the best model and operationalize it is one of the approaches that we have concentrated more on.
Thank you, Woodrow. We have a question from Kui. It is very informative. Just wonder if the AWS generative AI environment GXP compliant.
So there is obviously a lot of interest around regulations when it comes to generative AI. Our service, the Bedrock service specifically, is HIPAA eligible. So that allows you to ensure that any PHI information is whatever is coming into the models, and the response from the API is being used with PHI information. As far as GXP is concerned, I think there are ways in which we can work with regulators to actually provide guidance on how Bedrock adheres to certain particular particular parameters of GXP, like for example, reproducibility, or the ability for the models to actually maintain the same output with the same prompts. And there are controls within Bedrock that allow you to do that in a very confident way. But I think everyone's view on GXP when it comes to generative AI is very different at the moment. So we ourselves are trying to come level set on what the industry wants as far as GXP is concerned. One thing that I can tell you confidently is we are working directly with the source. So our public policy team is working directly with people who are making these policies around GXP for generative AI in the FDA. And you'll see a lot coming out from that group that will then be translated specifically into rules that we include within services like Bedrock.
Thank you, Ujjwal. We also have Peng Yang, who is our VP strategy here from Dashu. She is asking, can you give a pharma industrial example of Bedrock-based project?
Yeah, so we recently actually published a use case with Eversana, which is in the commercial space. And they are using Bedrock for a lot of their pharma commercial use cases. So right from document summarization to finding out what their sales and commercial team should actually concentrate on. They're also using it for campaign generation. So if there are certain drugs and those drugs are marketed at different countries, there are ways to localize those campaigns based on the regions and the countries that it's marketed in, and all of that are things that are being offloaded into generative AI.
Thank you. I know we are running short on time, and we're going to get to several questions. So Dan Long asked, do you have experience to use LLM to handle different agents that imitate different person to do different things?
Yeah, absolutely. So we are actually experimenting with that a lot, because I think that's where I think the future of these LLMs are. As we see the number of parameters increasing, it's very hard for that model to scale to the level of human accuracy if it's not broken down into different smaller models that can be orchestrated with an agent-based approach. That's where I think the field is headed. We have created certain prototypes that, like I was explaining earlier, that you can create an agent to interact with data stored in Health Lake, Omics, and imaging, and then have a chatbot that can answer questions across all of these. So based on the question, it can understand where it needs to go fetch the information from. So the way we have designed this is, you can take that question and LLM will then break that question. And based on the tools that are registered in the agent, it can then choose the right tool to fetch that answer. So let's say if you ask the question, what are the medical conditions that a particular patient has, and you have a tool for EHR, then that model will then break that question down into a tool that, oh, I actually need to use a tool to fetch that information. It'll go fetch it, and then it'll summarize it for you and give you an answer. So that entire chain of thought, as you call it, is managed with Bedrock agents really well. So you can start experimenting with that. It's also a very new and upcoming field. So I would recommend continuous iterative development with it. Our prototypes are very encouraging, and we are just waiting for more and more of these to come out in research to validate our approach with something that we can launch in production.
Thank you, Ujjwal. I know we're running short on time, and let's have one last question. First of all, Jiying is our volunteer in Dashu. Jiying, I'm going to hand over your question privately to Ujjwal. Let's address Haonan's question. I have a relevant question related to that. Sorry about that. It's a great topic. So from Haonan, do you have experience to establish, I think it's a unified generative pre-training workflow, specifically for non-sequential omics data? And then, Ujjwal, my next follow-up question regarding omics data, I do know that you have AWS Health Omics initiative built underneath AWS. We generate tons of RNA, DNA, and H&E scannings from our clinical development as well. If we want to implement health omics as an organization, how fast can we actually start? Day one, can we wrap up in the infrastructure to deploy the AI ourselves? So starting with the unified generative pre-training workflow question.
Yeah, so when you say unified generative non-sequential genomic data, so one of the I don't have a chance to ask you a follow-up, but maybe one of the things that we have been doing is considering genomics not just from the point of view of genomic sequences, but also from the point of view of annotations of different variants in external data stores and correlating that with phenotypes, right? So now you have, your raw genomic sequences, you have the variants in a variant data store, and then you have the ability to, let's say, annotate them with external data sources like ClinVar. So you have a very holistic picture. And with generative AI, you can go from finding your references or your alleles and then going into variants that actually do not match certain references, so find mutations and then find specific clinical conditions that are associated with that mutation. If that's what you're meaning by workflows that do not rely on entirely on sequences, we are very actively looking in that space. And I think agents is a very good seg to that, because with
Mhm.
agents, you can then get into each of these modalities and answer questions, across them, not just relying on the sequential data. So I don't know if that's what your question was, but hopefully, it gave you some answer. And then how easy it is to use Omics, it's extremely easy. I mean, that's one of the things that we have ensured when we launch services. All you need is an AWS account, and you go in and you'll find very detailed instructions on how to load your variant information, your raw BAM, CRAM files into, Omics.
Mhm.
And then what we have created is something called workflows within Omics.
Mhm.
So once you have all of that data stored, then you can like kick off workflows for, let's say, variant analysis, secondary analysis of converting raw genomic data into VCF files, and then visualizing them into dashboards, and then doing machine learning on all of that using managed workflows. So that entire thing is completely managed. Of course, it integrates with the whole of AWS ecosystem. So once you have that data over there, then you have the ability to use a lot of our tools that I didn't mention today in my
Mhm.
presentation.
Understood. Okay, great. Thank you, Woodrow. I know we're way over time. We really appreciate the efforts that you can come to give a great talk to the Dasher community. This talk is already being recorded. It will be uploaded to our YouTube channel, and we welcome you to come back again in the future if possible. Thank you, Woodrow, for your time. Thank everybody for attending today, and thank you, Beijing folks, for sponsoring today's event. And I'd love to meet you all in the future. Thank you very much.